Hello and welcome back to Principles of Thermodynamics. In our last video, we talked about how to read thermodynamic tables. Now, however, the tables are very limited. They can't tell you every single value that you might want to look up. So, for instance, let's just say I wanted to look up what superheated refrigerant R134A is. That's this R134A was at the pressure equaled 1 megapascal, the temperature equaled 63 degrees Celsius, and I would ask you for what was its enthalpy. Well, you'd have a tough time doing that because the tables a table that you would have of refrigerant R134A would not have a 63 degrees Celsius part to it. It just would not be cataloged in that table. So what most people do is do something called linear interpolation. It's a very important skill to know, and it will be coming up throughout a lot of thermodynamics, so it's an important skill to master early. Now, what linear interpolation is, basically, is let's say I have some graph, and I have 2 points that I know. Now this is a y-axis, this is an x-axis. This is x1, this is y1, this is x2, this is y2. And there's some point in the middle. Now I'm assuming that there's a linear relationship between point 1 and point 2. It may not exactly be linear, but especially when you're working with thermodynamics, the difference between the actual correlation between 2 points that are very close together is so close to linear, we can just assume it to be linear. So there's this other point in here, and we know its x-coordinate. We are given it, in this case, if we were to relate it back to this problem, 63 degrees would be our x value, and enthalpy would be our y value. But let's just focus on the theory behind linear interpolation first. So we have an x that is known and a y that is unknown. So if we're assuming that this is a line, then it has some slope. But we can also say that the slope of A equals the slope of B. These are 2 parts of the same line. Therefore, the slope is going to be homogeneous. All throughout, it's going to be the exact same. So half this line is going to have the same slope as the other half of the line. Therefore, now if you remember, slope equals y2 minus y1 all over x2 minus x1. So let's put it back in terms of this. So that means y1 minus, y2 my y minus y1 over x minus x1 equals y2 minus y over x2 minus x. Now this right here is the slope of A. This is the slope of A. And this is the slope of B. And we just set them equal to each other. Now, don't forget, every one of these points is known except for y. These 2 values are the only unknowns. They're the only variable in this entire equation. So what we do is we're going to solve for y. Now this is just going to be a lot of algebra, and if you want me to do a video in which I do out the algebra, I will. But for now, I'm just going to do some hocus pocus and tell you that y equals y1, the initial state of y, plus x minus x1 times y1, y2 minus y1 over, y1 over x2 minus x1. Now, what this is essentially doing is saying that this y is just, we start at this point of y1, and we are adding, we're going up along this line because this is going to be some x, and this is going to be the slope. This is the slope of the entire line, as you can see. This right here equals this right here. And then this is just what, this is just the difference of these x's. So we're just creating we're mostly just looking at a right here. This is, yeah. And that is how you would solve for y. So let's do this in terms of thermodynamics. We have refrigerant R134A that we're looking at. The example I gave you, the pressure equaled 1 megapascal, temperature equaled 63 degrees Celsius, and I asked you to look for its enthalpy. So what we're going to do is we're going to look at the thermodynamic table for R-134A, and we're going to look at its 1 megapascal table. And what we're going to do is we're going to look at the two entries of it for temperature that that include 63 degrees, the smallest, the two closest that we can find to make our linear interpolation estimate more precise. So I look at the table and I see that we have 60 degrees and Celsius and 70 degrees Celsius are the two closest entries that house the 63 degrees Celsius. So I'm going to look up 60 degrees Celsius and 70 degrees Celsius. And what I want out of there is its enthalpy. The enthalpy at 60 degrees Celsius and 1 megapascal of refrigerant R134A equals 291.36 kilojoules per kilogram. And at 70 degrees Celsius, the enthalpy of refrigerant R134A equals 302.34 kilojoules per kilogram. Now, because we're assuming a linear interpolation, there's not going to be any wild variance between these two. We are going to assume the enthalpy that we're looking for is going to be in between these two. So somewhere in between these two values is going to be 63, the enthalpy of 63 degrees Celsius. So if you recall from just a minute ago, we have y equaling y1 plus x minus x1 times y2 minus y1 over x2 minus x1. So, in this case, x we're going to be treating as the temperature, and y we are going to treat as enthalpy. So in this case, x equals T, y equals H. They're just variables, they don't really care, we don't really care what letters we use. So the H that we're looking for is going, oh, and we're also going to mark this is 0.1 and this is 0.2. You can reverse them and get the exact same answer. It's just going to be easier to work with this. So H equals 291.36 plus 63 minus 60 times 302.34 minus 291.36 all over 70 minus 60. Now, if I just take out my calculator, which is my iPod because I don't know where my calculator is, this is going to equal 294.55 kilojoules per kilogram. And that is how you do linear interpolation with a thermodynamic table.